Gas exchange and concept of partial pressure and diffusion. What are some things that affect the diffusion rate of a gas? What are some things that affect how quickly gas diffuses across, let's say, the lung wall into the blood? Pressure gradient would be one. I can think of about 4 or 5 or 6. Diffusion distance is one, but more specifically probably the thickness of the membrane. Okay, if the membrane is thicker, diffusion rate of a gas goes down. Okay, so we have pressure gradient, we have thickness of the membrane. What else? How about the cross-sectional area for diffusion? Somebody with emphysema, their lungs, they lose diffusion area, so their gas exchange is impaired. Less oxygen gets into the gas. Okay, besides that, there's also the solubility of the gas. The more soluble a gas is, the easier it diffuses. Which is more soluble in water, oxygen or CO2? CO2. CO2. It's about 20 times more soluble. So CO2 diffuses across the lung wall into the blood, or vice versa. Actually from the blood into the lungs so you can breathe it out very easily. Oxygen, not so soluble. It takes a little more time to diffuse. And the other one happened to be the molecular weight of the gas. The bigger the molecular weight, the bigger it is, the harder it is. Think like a bug trying to get through a screen door. The bigger the bug, you can't get through the screen door. You follow me? Okay, same thing with gas diffusion. Partial pressure. The partial pressure of any gas is equal to what times what? Barometric pressure or atmospheric pressure, same thing, times the fractional concentration of the gas. And so when you go to altitude, what changes? Does partial pressure of oxygen change when you go to altitude? Yes, partial pressure would get lower. And why does it get lower? Is it because barometric pressure gets lower or the fractional gas concentration gets lower? Atmospheric pressure gets lower. So what's the oxygen concentration of room air right now sitting in the room? Ballpark. It's about 21%. If we went to Mount Everest, what would be the fractional gas concentration of oxygen? 21. Be about 21%. It's going to be the same. Let's talk about the oxyhemoglobin dissociation curve. Okay, for that I want to take a look at the graph. I'm going to turn on this light for a second. Okay, what I think will help you in terms of doing the stuff as far as the curve goes and what happens to ventilation is, I think when you get your test, at the top of the paper when you get these questions, is I would write this equation down, and then I'd also just draw a little picture of the curve. I think sometimes being able to visualize it really helps. Okay? So what I have here is I've got some variables and how they might change. And then I've got curve shifts. So we're talking about, does the curve shift to the right or to the left? And then we're talking about hemoglobin affinity. That's the strength of the hemoglobin magnet, how attracted the hemoglobin is to oxygen. Or another way to think about it is, what is the saturation at any PO2? Does it go up or does it go down when the curve shifts? Okay? How much oxygen binds to hemoglobin is dependent on several factors. One of them is arterial PO2. The more pressure of oxygen in the arterial blood, hemoglobin saturation goes up. And the way I explain to people to try to think about hemoglobin is think about hemoglobin as being like a magnet for oxygen. And the strength of the magnet can change. It can either be really attracted and really hold on to oxygen tightly, or it can be really weak and let go of oxygen, not be attracted very well. So as the partial pressure of oxygen increases, what happens to the strength of the hemoglobin magnet? It gets stronger, right? It wants to hold on to oxygen more tightly. Okay? The other things that can affect how much oxygen binds to hemoglobin has to do with the shape of this curve. Because this curve can shift and change shape and either shift to the right or it can shift to the left. Okay, what happens to hemoglobin affinity, or the strength of the hemoglobin magnet, if the curve shifts to the right? What happens to the strength of the hemoglobin magnet? Does it get stronger or weaker? If it shifts to the right, it gets weaker. And how you can tell is look at any PO2. What happens to saturation? So if I was here, and then the curve shifted to the right, and this is my new curve, what happens to saturation? It goes down. So the hemoglobin magnet, or hemoglobin affinity, now is low. And so it lets go of oxygen. So how much oxygen binds to hemoglobin is dependent on the PO2 of the blood, as well as the shape of the curve. Now, what are things that affect the shape of the curve? Temperature, pH, PCO2. These are the three things that affect the shape of the curve. There are some others that, for this class, we don't need to worry about. For this class, the main ones I want you to focus on are these. Okay? So let's talk about what happens when temperature increases. Which way does the curve shift? We're going to fill in this table, and you can either memorize the table or you can try to reason through it. And the way I reason through it is, where in your body does temperature increase? Exercising skeletal muscle. Okay? When we get into exercising skeletal muscle, do we want hemoglobin to hold on to oxygen tightly, or would we rather have hemoglobin let go of oxygen when we're inside the muscle that's exercising? We'd rather have hemoglobin let go of oxygen so it can diffuse to the mitochondria. Does that make sense? Okay, so which way would the curve have to shift for hemoglobin to become a weaker magnet, for hemoglobin affinity to go down? Would the curve have to shift to the left or to the right? To the right. So you can memorize the curve shifts to the right, or you can think about what is the logical response, and that's what the body does. In this case, it's the logical response. So the curve shifts to the right. So what happens to hemoglobin affinity? Hemoglobin affinity goes down when the curve shifts to the right. Saturation at any PO2 falls. Okay, same thing happens in reverse when temperature goes down. Temperature happens to be lower in the lung. You're breathing in outside air that's cooler than body air in normal situations. That cools the blood. So when the blood is in the lung, it's cooler. When blood's in the lung, would we rather hemoglobin grab onto oxygen tightly and load up with oxygen? Or would we rather hemoglobin let go of oxygen? We'd rather hold on tight. So that means hemoglobin affinity gets greater. And for that to happen, the curve would have to shift to the left. So at any given PO2, saturation increases. Does everybody see that? Okay, so in this case, when temperature goes down, curve shifts to the left, hemoglobin affinity goes up. Are we cool? Okay, let's do pH. When pH increases, does that mean you're more acidic or less acidic when pH increases? You're less acidic. Okay? When you're less acidic, that's the situation that would happen in your lung. Okay? Your lung is less acidic than, say, exercising skeletal muscle. In that situation, do we want hemoglobin affinity to be high or low? When we're in the lung, hemoglobin's in the lung, do we want its affinity for oxygen to be high or low? We want it to be high. So which way would the curve have to shift for affinity to increase? So it would have to shift to the left.